This video is going to talk about how we evaluate a classifier. So let's say we built some classifier. So far, we've only really talked about logistic regressions. Some of you may have seen my videos on discriminant analysis, but in the future, we're going to have many other classifiers such as neural networks and random forests, boosted trees, and so forth. So how do we evaluate that? So one possibility is just to look at the deviance. So the deviance is minus 2 times the log likelihood for a logistic regression. And that's one way to evaluate a fitted logistic regression model. Of course, we can't really compare it with a discriminant analysis model because the likelihoods are just fundamentally different. We don't really think of a likelihood in the case of a discriminant analysis model. Another possibility for logistic regression models is to use AIC. So we just take this deviance measure and we add 2 times the number of parameters as a penalized measure of fit. I'm not going to say much more about those measures. I'm going to focus much more on other measures based on the confusion matrix. So let's talk about those now. So one measure that often gets used is the classification rate. And by the way, the classification rate extends beyond just 2 classes. So a lot of what I'm going to say today only applies to the 2-class problem where I'm trying to predict, success or failure, buy, no buy, defect, not defect. But in general, you could have P classes where maybe I have 10 different digits and I'm trying to classify a handwritten digit as one of those 10 digits. So the classification rate will work there as well. So what is the classification rate? It's just the percentage of correctly classified cases. So if I have 100, say, training samples, and my classifier gets 90 of the 100 correct, then my classification rate is 90%. The misclassification rate is just 1 minus the classification rate. So if I got 90 right out of 100, my misclassification rate is 10%. So the classification rate is computed from what's called the confusion matrix. Now, I want to just click on this for a second. I've given you a link to Wikipedia. And so Wikipedia, if you scroll down, gives an excellent expanded version of this classification rate, this confusion matrix, which I encourage you to look at. This is extremely comprehensive. I'm going to talk about many of the statistics here, but not all. And if you're interested in some of these other ones, go to the Wikipedia page for a slightly more comprehensive treatment of this topic. All right, so here's the idea of a confusion matrix. I know the actual class of each item. So every item is either actually good or it's actually bad. So if I have a classifier to predict whether or not someone clicks on a banner ad, those visitors who actually click on it, those are the actual goods. The people who do not click on it are have a dependent variable value of no. So those are the actual no's, or the actual bads, if you want. Now my classifier is going to make a prediction for each one of my sampling units. So my classifier either predicts that the unit will be good or bad. So this could be buy, not buy, click, not click, and so forth. Now, this crosstab, or two-way table, has 4 cells in it. So the 4 cells are simply the true positives. So true TP is the number of true positives. So these are cases that are actually good, whatever good means, and my model classified them as good. True negatives are the number of cases that are actually bad, and my model got it right. Now there's 2 other possibilities. The false positives equal the count of actually bad cases that were predicted good. So this false positive language comes from medicine, where you actually don't have the disease, which I guess is not a bad thing, it's a good thing, but you don't have the disease, but the test says you do, so the test is like your classifier, predicts that you have the disease, and that would be a false positive reading from the test. If you're actually good and you predict that it's going to be bad, that's called a false negative. So this would be where you actually have the condition, but my classifier misses it. So you can see where the classification rate comes from this confusion matrix. I just add up the diagonal elements and divide by the total elements, which is just the sample size n. The misclassification rate would be the false negatives plus the false positives divided by n. Now there's a few other statistics that we commonly compute from a confusion matrix. So I have to warn you that there are many different fields use the confusion matrix, but every field has its own name for the different conditional probabilities in the confusion matrix. So in machine learning, the term recall gets used. In medicine, the exact same thing is called the true positive rate. In other fields, you will see the term sensitivity. So what is this? What is the recall or true positive rate of a classifier? Well, recall is where we predict it's good when it's actually good. Now, I love the term true positive rate because it describes what it is. Of the actually good cases, which ones did my classifier get right? So the way to think about computing this is we're going to take the number of true positives and divide this by the number of cases that were actually good. So take the false negatives plus the true positives. So it's just a row percent. Think of it as a row percent, and you get this true positive rate. Now let's just go back to Wikipedia for a second, and you can see that there's they've organized their table. They transposed their table. But okay, so there's true positive, recall, sensitivity, the probability of detection, the power. All of those terms mean the same thing. Let's just stick with true positive rate and recall, given the nature of this class. Now, another really important conditional probability that we can compute off of this is called the false positive rate. So the false positive rate, I think, is pretty self-explanatory. It's how many times does my model predict something that's good when it's actually bad? So this is also going to be a row percent. We're going to just focus on this row of the table of those that are actually bad. So add up the true positives and the false positives. What fraction does my model get wrong? So that would be the false positives divided by that rate. And so we can go back to Wikipedia. False positive rate has fallout rate, false alarm rate if you're doing quality control. Those all mean the same thing. All right, back to my course packet. I'm going to give you one more conditional probability that's very important, especially in machine learning. This one gets used all the time in machine learning. It's called the precision. So precision is going to flip these conditional probabilities around and say, of the actually good cases out there, what fraction does my model find? Okay, so in the case of a recommender system, how many of the recommended items, which ones are ones that you're actually good at, do you actually like? So of the recommended items, what fraction are relevant? So let's go look at this. Of those predicted good, that would be the total of this column. It's what fraction of the good ones, what fraction of these predicted good ones are actually good. So TP divided by FP plus TP. All right. Before I, all right. There's an additional complication that we need to worry about. And so the complication is this. What is a a predicted good item. So in the case of a logistic regression model, what comes out of the model is a predicted probability. So it's a number between 0 and 1, where 1 is 100% probability that you have the condition. 0 is there is no chance that you have the condition. But the model really gives us numbers in between 0 and 1. So the model might say there's a 70% chance that you're going to buy from me today, and a 30% chance that you don't buy from me today. So where do I make the cutoff in order to make my confusion matrix? Because the confusion matrix is binary. It's either predicted you're going to buy or not buy. Well, I think the obvious answer to this is we have to pick some cutoff value C. So any predicted probability greater than C, we call a predicted good case. Any predicted probability less than C, we call a negative or bad case. All right, now this raises yet another complication, which is how do we pick C? What I'd like to argue with you is that this should depend on the misclassification cost. All right, so what is the cost of a false negative versus the cost of a false positive? So just to give you a couple examples of this, let's say I'm building a spam filter. So positive means this email is spam. Negative means this email is not spam. Now, let's think about the cost of a false positive. So a false positive in my spam filter example would be the email is classified as spam when in fact it's a legitimate email. So it gets sent to my spam filter and I never see it, but it's actually a good email. So what is the cost of a false positive? It could potentially be very high. So maybe my boss has sent me an important email and it got sent into the spam filter and I never see it and never respond, and therefore my boss gets angry with me. On the other hand, what's the cost of a false negative in the case of a spam filter? Well, the email gets through and I have this spam email sitting in my inbox. Hopefully I don't open it and get a virus or something. I just hit delete, and so the email's gone. All right, so in that case, I would argue the cost of a false positive is much higher than the cost of a false negative. And therefore, I should set this cutoff or threshold C to be very high. I want to be really sure this is a spam email before I put it into the spam filter. All right, now let's consider an alternative setting like airport security screening or maybe breast cancer screening. So let's say we have a patient who comes in and needs a breast cancer screening treatment. And let's think about the cost of a false positive. So the false positive would be the test says you have breast cancer when you don't have breast cancer. So this is going to cause some stress, but you'd have to go for maybe a higher level of screening where that higher level of screening would have a lower misclassification rate. And so I would say the cost of a false positive is much lower. Likewise, if you're doing airport security screening, a false positive would be the metal detector goes off and you have to have some additional screening. I'd say the cost is quite low. Alternatively, what is the cost of a false negative? So false negative in the case of breast cancer is you have the disease, but the test doesn't detect it. Okay, so the test is giving a false result that is negative. Well, in this case, you could literally lose your life as a consequence. Likewise, with an airport security screening function, a false negative would mean this person really has a weapon and you let the person through. That'd be a false negative. So I hope you will agree with me that the cost of a false negative far exceeds the cost of a false positive in those instances. So we would want to set the threshold very low compared to what we would for a spam filter. All right, we're going to see some curves that help us make these decisions in a minute. Next, another statistic that gets reported is sometimes called the F1 measure. So F1 is just the harmonic mean of precision and recall. So the higher this is, the better your classifier is. And so that's commonly computed. Another plot that's often generated is called the precision recall plot, where you plot all the precision values versus the recall values for different values of C. One more extremely useful plot is called the receiver operator characteristic curve, otherwise known as the ROC curve. So a couple things. The Wikipedia page is excellent, and you're going to see the exact same table that we saw before. And there's an excellent article that I would recommend reading if you have more interest in the subject, that talks about how you actually compute these and walks you through many very interesting examples. All right, so what is an ROC curve? So an ROC curve is similar to one of these precision recall plots, but we're going to plot the true positive rate against the false positive rate, varying the value of C. I'm going to just give an interpretation now, and then we're going to see an example where this will become clear. So I'm just going to give you the rules now. We usually compute the area under the curve, under the ROC curve, and that's called the AUC measure. You need to remember this, and so this will become very clear in a minute. AUC of 0.5 means random guessing, and you have an absolutely worthless model that doesn't contribute anything. AUC of 1 is what I call the crystal ball perfect classification model. So if you have an AUC that's close to 1, that means you got a really good classifier. Anything that's down near 0.5 is really bad. And in a minute, I'll tell you about AUCs less than 0.5. So let's look at an example, and then we're going to kind of illustrate all these things through the example. So we're going to go back to our defaulting customer data, and remember that we're trying to predict whether or not some person who just joined a fitness club cancels the membership in the first 3 months. So if we look at the data, what you're going to see is the distribution of the dependent variable, so do you default or not on your membership, is that there's about 12% cases where the customer defaults, 88.3% where they don't default. Now, let's begin with a very stupid classifier. So my classifier could be this. Anybody who comes in, we're just going to say they're not going to default. All right, so everybody is a no. My classifier predicts no for all cases. Well, it should be kind of impressive that this classifier is right 88.3% of the time. I mean, wow, that's really good. But of course, this is stupid. So I want to point this problem out. This is a problem called the Class Imbalance problem. So the Class Imbalance problem gets a lot of discussion in various machine learning books because often you're up against this. So if you're trying to predict whether or not someone has diabetes, very low percentage of people in the population have diabetes. So if you just say nobody has diabetes, your classifier is right 99% of the time or so, when in fact it's not a very good classifier. Or in the case of say fraction of people who click on a banner ad, 99-point-something% don't click, so it's horribly imbalanced. So we're gonna have to deal with that. So I'm gonna build a model now where I've fitted a logistic regression model with down payment, payment type, use, age, and gender in it. So we now have fitted values, and I'm going to try a cutoff a 0.5. So anybody who has a predicted probability of 0.5 is labeled a predicted defaulting customer. Anybody who has a predicted probability less than or equal to 0.5 is called a non-defaulting customer. So I can make a confusion matrix with just the table command. So let's be consistent with my confusion table before. I'm going to put the true value. So these are the actual values. So the customers who actually default are in this row. The customers who actually don't default are in the top row. And then across the top, we have our fitted values. And I'm just going to, if the fitted value is greater than 0.5, you're called a true. So true in this case means my model says you're going to default. False means my model says you're not going to default. So how do we compute the classification rate? Well, remember the classification rate is the sum of the diagonal elements. So 21,468 plus 818 divided by the total number of cases, which is about just under 25,000. So notice I'm at an 89% classification rate, and you might say, well, that doesn't look much better than 88.3, and you're right. And so we really need to start looking at some of these other measures, the true positive, false positive, precision recall measures. So let's go look at the true and false positive rates. We can compute these with the prop table command. So prop table is a proportion for a table. It just computes either the row percents or the column percents. So if I say prop table with value 1, so 1 means condition on the first coordinate. So remember, we always, when we specify a matrix, we give the row then the column. So x comma I, x sub ij, I is the row, j is the column. So here we're saying I want a condition on the rows. So as a quick example, if I look at all the true positives, so these are, well, all the positives, the people who actually default, you've got 2105 plus 818. And if I take 818 divided by that sum, I get 28%. If I take 2105 divided by that sum, I get 72%. So the correct interpretation of, let's just take this number, is as follows. I would say 28% of the people who default are predicted by my model to be bad. So of the true cases, of the true positives, my model's right about 28% of the time. So that's the true positive rate. Let's go look at this number. So this is going to be the false positive rate. So these are going to be, of all the cases that did not default, 2.6% are predicted by my model to go away. Okay, so the false positive rate is this number, the true positive rate is this number. I'll just mention that if you, I'll leave this as a little exercise for you. If you do prop.table with a 2 here, you're going to get the column percents instead of the row percents. And so remember, precision is one of those column percents. So I'll let you do that on your own. So I want you to remember, true positive rate is 28%, false positive rate is 2.6% when you have a cutoff of 0.5. Well, what happens if we change our cutoff? So I'm going to make it easier to label a case as positive. And so we're going to reduce the cutoff to 0.3. And so if you do this, notice your classification rate is now only 88.8%. So we're only beating this stupid classifier by 0.5%. But look what happens to my true positive and false positive rate. Now these things are immune to the problem of class imbalance. So I say that down, I guess that was a question, but I'll tell you the answer. They're not affected by class imbalance because we're only looking at the positive cases at one time and only the negative cases at one time. So it doesn't matter what fraction are positive or negative because we're conditioning on the rows. All right. So when we look at this, the true positive rate is 67%. So of the actual defaulters, my model gets 67% of them right, but I pay a little bit of a penalty because of the negative cases, my model falsely says they're going to default 8.2% of the time. So I've just computed true and false positive rates for 2 values of C. Let's go do that for many other values of C. So I've done this in this code up here. If you're interested, you can go look at the code, and we get the following curve if you do that. So I'm plotting the true positive rate and the false positive rate for all the different values of C. So let's take one of the values of C, which is 0.5. So remember, I said the true positive rate was 27%. The false positive rate was about 2.8%. I think it was what it was. And that's the value of that point. Then we went off and we did it for C equal to 0.3. And our true positive rate shot up to about 67%. False positive rate was around 6 or 7 or 8%, something like that. And so that's what the value of this horizontal coordinate is for that. Let's just think a little bit more about this. So if I dial the threshold way up, okay, so I make it extremely hard to ever declare a case positive. I need a predicted probability greater than 0.9. What happens? Well, notice I make no mistakes. So there are no false positives when I have a very high threshold. Unfortunately, I also don't find any positive cases, so I never detect anybody who's going to cancel. Now, as I reduce this threshold, what you're going to see is that the true positive rate increases pretty quickly. So I can easily catch 70% of the cases here. And what's important is that I don't have a lot of false positives. Okay, so I can find 70% of all the positives out there without making too many false positives. Now beyond 70-80% here, then my false positive rate starts to increase very rapidly. So it's really hard to get all the positives without catching a lot of false positives. Now, I'm just going to go over to my scratch pad for a second and draw a couple pictures. So remember, here's the true positive rate. Here's the false positive rate. The ideal classifier would look something like this. I could catch 100% of the true positives. So this is 100% true positives, 0% false positives. That would be the ideal classifier. And if I could do that, this would be my ROC curve. So it would just be up here, and I would have an area under this curve of 1. So I like to call this the crystal ball classifier because I can it's like I can see perfectly into the future whether or not you're going to default, and my model just gets it right all the time. Now, on the other hand, if my classifier looks like this, so if the true positive rate increases at the same rate as the false positive rate, I'm just doing random guessing. Gotta spell it right. Guess. Guessing. Yes, I do know how to spell guessing. The area under the curve here would be 0.5, and that means your classifier isn't helping at all. Now, I thought I would just draw one more picture for you. What happens if you had something like this? So let's say your classifier looks like this, and the AUC is maybe 0.1. Well, this is a really bad classifier, but it's actually a pretty helpful classifier. So what this is saying is your classifier is almost always wrong, but it's wrong so often that if you just do the opposite, so whatever your classifier says, assume it's the opposite, you're going to be right very often. All right, so this is a very bad classifier that could actually be good if you just kind of change the definition wherever your classifier says bad, make it good. All right. There are other interpretations of AUC given in this article. All right, the last thing I want to cover with AUC is a little bit more about how it's actually used. So we use this very often when we want to compare models. So we've built different classifiers. Maybe I have a neural network and I have a logistic regression and I want to say which one is better. We would use ROC curves. So just to illustrate this, I have fitted a logistic regression using quite a few predictors, and then I have a second logistic regression model where I got rid of a couple of the power predictors. Okay, so this is like the model that more parsimonious, but then the question is, are my predictions worse if I get rid of those variables? All right, so you'll see fewer variables in fit 2. Now there's a library in R called PROC. So I guess I don't know where I should have brought that in. Let me go over to the Scratchpad for a second and just write that out. The way you would say PROC. So in R, you would type this command. I'll add that to the course packet before I distribute it to class. So it's little p, big ROC. This is a pretty useful library for computing AUC and generating ROC curves. I hope you can read the help page on this. You give it the true values, you give it the predicted values. I don't like the axes that are given by default. I like the legacy axes because they're consistent with TPR and FPR. They call them sensitivity and specificity. You can use XLab and YLab if you want to change those, which is kind of what I did here. Then a couple other options that you're going to find useful. Print AUC tells whether or not to print the AUC value, and then you can give coordinates of where you want to print it. Another thing that you can do is specify a color. So model 1 is black, model 2 is red, and what you'll see with these two models is the black curve dominates the red curve. So for any point, so for any, say, true positive rate, let's just fix the true positive rate, I'm better off with the black model. Why? Because I have a lower false positive rate with the black curve than I do with the red model. If I chose another value, if I wanted to get more true positives, at this point, I have fewer false positives with the black model versus the red model. If I keep going, you're going to see the black model always wins. If we go back to the article, you're going to see they give some slightly more, more complicated setting where you have 4 models, A, B, C, and D, and different models win in different regions of this ROC space. So model A wins in this area, then you're going to see model B wins, then model C wins if you want to find all the positives or most of the positives, and you're going to see model D never wins. Model D is dominated by one of the other models in all regions of the space. All right, so that's it for this lecture on AUC ROC values.